Welcome to the Explainer. So today, we're not just going to be crunching numbers, we're actually going on a journey. We're going to explore this really revolutionary idea, a whole new dimension for numbers.
All right, let's just dive right in. You know, we all remember the number line from school, right? Positive numbers go this way, negative numbers go that way. It's flat, one-dimensional. But what if, and this is a big what if that's only half the story? What if numbers could go up and down too?
You know, for centuries, the square root of -1 was just impossible, a total dead end. But then some clever mathematicians decided, hey, what if we just give this impossible thing a name? And they called it I. And with that one little move, they didn't just invent a new number. Oh no, they unlocked a whole new axis, a vertical one, turning that flat, boring number line into this rich, two-dimensional map. We call it the complex plane.
Okay, so we've got this incredible new 2D world for our numbers. What now? I mean, what are the rules here? How do you even navigate this thing? Let's take a look at the basic operations. You can think of them as kind of like the rules of the road for this new mathematical landscape.
So every single spot on this new map has an address, right? And that address is a complex number. It looks something like A plus BI. Now, the A part, that's the real part. That's just how far you go left or right, east-west. And the B part, that's the imaginary part, how far you go up or down, north-south. So just like the source material shows, a number like 2 plus 3i isn't some weird abstract thing. It's just a set of directions. Hey, start at the center, go 2 units east, then go 3 units north. That's it.
And this leads us to a really fundamental rule, which comes straight from question 12 in our source material. And honestly, it's just plain logic. For 2 pins on a map to be in the exact same spot, well, their east-west coordinates have to match, and their north-south coordinates have to match, right? You can't be in the same place if one of them is off. And it's the exact same deal with complex numbers. The real part's got to be equal, and the imaginary part's got to be equal. Simple as that.
Now, division looks scary, right? Like in question 11 from the source. I mean, how do you even divide by a 2-part coordinate? Well, there's this really clever trick, and it's all in step 3. You multiply the top and the bottom by something called the conjugate. And all that is you take the same complex number from the bottom and you just flip the sign of the imaginary part. The magic here is that this little move always gets rid of the I in the denominator. It just vanishes and it turns it back into a simple, regular old number that we already know how to deal with. It's a fantastic little trick.
All right, let's keep going and see where this all leads. Because now that we've got the basic rules of the road down, we can start to appreciate the really beautiful part of this whole world, its geometry. This is where it all clicks. This is where algebra stops being just symbols on a page and starts becoming about shapes and distances and angles.
So here's the crucial point. When a problem, like question 14, asks you for the modulus, it sounds complicated, but it's not asking you to do some crazy calculation. It's really just asking a simple question. If you tied a string from the very center of your map, from 0, right to your number's location, how long would that string be? That's it. It's just the distance.
Okay, so if the modulus is the distance, then the argument is simply the direction. Imagine you're standing at the center of the map and you're facing east, along that real axis. The argument is just the angle you have to turn to be pointing directly at your number. That's all a complex number really is when you get down to it, a distance and a direction.
And this is where the geometry just gets absolutely mind-blowing. As it's shown in question 20 from the source, when you multiply any number by I, something magical happens. It doesn't change how far the number is from the center, the modulus, the length. It stays exactly the same. All it does is rotate it, a perfect 90-degree turn counterclockwise. Just think about that for a second. Multiplication by I is rotation. That is so cool.
Okay, so let's see how we can use this to draw things. We can use equations to describe entire shapes on this map, and the source material calls these loci. Now, loci is a fancy word, but it's just a set of points that all follow one specific geometric rule. And with complex numbers, we can write down those rules as these really elegant little equations.
Let's take this equation from question 18. What it's saying, in plain English, is find all the points z where the distance between your point z and the point I is always exactly 2. So, what kind of shape do you get if you plot every single point that's the exact same distance from a central point? You get a perfect circle. See? The equation is the circle.
All right, now this one looks a bit more complicated, but the geometric idea behind it is just as elegant, I promise. It says, Find all the points z where the distance from z to negative 2i plus the distance from z to positive 2i always adds up to exactly 6. And if you remember your geometry class, that is the classic textbook definition of an ellipse. It's the set of all points where the sum of the distances from two fixed points, the foci, is constant. It's amazing. Again, the equation is the
Okay, so once you really start thinking this way, in terms of distance and direction and geometry, you suddenly unlock these incredibly powerful shortcuts. These are the tools that make problems that look really complicated, well, they become elegant and, honestly, pretty simple.
So in question 16, the source material gives us this ridiculously powerful shortcut. When we stop describing numbers by their east, west, north, south coordinates and instead use their distance and direction, which is called polar form, these really hard operations just become trivial. To divide two big complex numbers, all you do is divide their distances and subtract their angles. That's it. No more messy algebra, just simple arithmetic.
All right, now just look at this thing. This is a monster. At first glance, this problem from question 17 looks, it's practically impossible to do by hand, right? You'd have to expand all of those powers, do that massive division. It would take you pages and pages of work.
But here's the beautiful trick. We don't actually need to calculate that final messy number. The question only asks for its modulus, its total length. And here's the shortcut. The length of a product or a division is just the product or division of all the individual lengths. We can just break that monster apart into little easy pieces.
And so when we actually apply that rule, something truly amazing happens. We just calculate the simple length of each little piece, like the length of 1 plus 2i is just the square root of 5. We do that for every single part, we apply the powers, and all the terms, they just magically cancel each other out. And what are we left with? A final total length of just 1. An absolutely impossible-looking problem becomes simple. That is the power of thinking geometrically.
So, okay, after all of this, the plane, the geometry, the rotations, you might be sitting there asking, why? Why does any of this actually matter? Why do we need a second dimension for numbers anyway? What's the point?
Well, our little journey here has taken us from a flat, one-dimensional line into this whole 2D plane. We've literally turned abstract algebra into intuitive geometry. And this new language, it's essential. Because so much of our universe doesn't just move forward and back. It rotates, it vibrates, it oscillates. This is the mathematical bedrock for electrical engineering, for signal processing, and even for the strange, beautiful world of quantum physics, where it literally helps describe the fundamentals of reality itself.
And that just leaves us with one final thought. So many of the most important things in our world, from the electricity that's powering your screen right now to the very nature of light, they're not linear. They have this other component, a phase, a rotation. And complex numbers, they give us the language to describe that hidden dimension. It really makes you wonder, doesn't it? What other secrets are out there, just waiting to be described, that we can only find if we're brave enough to venture off the number line?